So who's heard of GD&T before? Geometric dimensioning. Let me see. Can I see you? I got my safety glasses on, so you guys can throw stuff at me today. I will be safe. So you've heard of GD&T before. What do you know about it? It's on a lot of mechanical drawings. It's probably on every mechanical drawing at some level. So it's a system, right? So it's a system for, is it a system for tolerancing the parts? Because you said it was a system for tolerancing the parts, but I'm pretty sure it's a system for representing what the tolerances are and what the dimensions are for the parts, right? So it's a standardized way for designers to tell manufacturers how they expect the part to be made and what they expect the part to fulfill. So anyone could design something, right? Anyone could design something, and anyone could pick the dimensions that they want, and anyone could pick the tolerances, and then you could like write a story about it. So you could just get out your journal and say, well, the 2x4s should be 6 feet long, and you could put in all this detail about everything, and you could then send that off to somebody else, and they could read your story, and they could try to make the part. Is that true? Is it possible? In order to get something made, do you have to always adhere to the standards for GD&T? Who's ever made something without making a drawing first? So about a third of the hands are up. About a third of us have made something without making a drawing first. Who's ever made something without designing it first? A lot of us have made something without designing it first. We've got a concept, but a concept is just the idea of the thing we want. The design actually represents that thing in such a way that we could give it to somebody else and somebody else could make it for us. And so the reason we do this GD&T, this geometric dimensioning and tolerancing, oh, look, it worked. The reason we do it in certain ways is so that we can communicate our design to somebody else so that somebody else can make it. If we're doing the design, we're making the part. If you're doing your MQP, for example, and you're the designer, you're the manufacturer, and you're the customer. If you're wearing all of those hats for the part, you don't have to follow all of the standards. The purpose is to communicate with yourself. We've talked about spelling in the class before, right? And the fact that I ain't got none. I ain't got no good spelling genes. But if I write something and you understood what I meant, I communicated. The problem is when I write something that's ambiguous, and it could mean one thing to you and something else to you. And then maybe both of you are making my parts for me. And you both give me different parts. And I say, but neither of these parts work. So I get them back and I say, they're all junk. Your parts are no good. Your parts are no good. It's all junk. And I'm not going to pay you guys. And you say, hey, we made it exactly the way you said to on the drawing. And so then what happens next? So if you made me the parts and you said you made them exactly the way the drawing said, and I get the parts back and I said these parts are junk, I'm not going to pay you. What happens next? Scrap, no good, does not meet my need. I'm the customer, I want the parts to meet my need. I ordered the parts, I got the parts, I put them into whatever I was building and they don't meet my need. What do we do next? Well, it's all right. So you say it has to do with quality, but he says he made them exact to the drawing. He says, I got your drawing right here. I measured the parts. We made the parts exactly the way you drew them. So what happens next? We tell them, like, to order a new part for a specific cost specification, Yeah, so I mean, there's a couple things that could happen at this point. You as the vendor could say, "Oh, big billion-dollar company customer, we'll make you some new parts, and we're really sorry we screwed up, and we'll never do it again," right? Or you could say, "We got enough lawyers to take this guy on. We're going to court," right? And you could court arbitration. You could get in something where you're discussing whether or not the parts meet the tolerance, right? And it's really going to depend. Was it a $500 job, or was it a $50 million job, right? Somewhere in between there, you're going to decide to get the lawyers and go to court. The reason we use standards and tolerances, or standards and this GPS system or the GD&T system, is so that when I, as the customer, make my drawing, I reference a particular standard and say, this drawing conforms with this standard. You, as the vendor, when you receive that drawing, if there's something you don't understand on the drawing, you can refer back to the standard to say, what does that symbol mean? What does this tolerance mean on this thing? And now we have a rule book to play from. And it's much harder for that misunderstanding to happen. But I could say, I could put out my drawing, and it could have something that's, I know exactly what it means. And in-house at my company, we do it this way all the time. We always represent it that way on the drawing. We know what we mean when we say that. Could mean something else to you. So these GD&T are standards. Of course, we have competing standards. The American, so ANSI and ASME have their own standard. It's the Y14 geometric dimensioning and tolerancing standard. And ISO 213 has their dimensional and geometric product specification. They call it GPS. It's really funny. They released the new GPS standard, the ISO GPS standard. And we're all like, all us Americans are like, really? Because GPS means something else. But anyways, it's a book. It's a book with rules in it. Rules about how you represent things on drawings. And there are some people that are really good at teaching you how to use the book and how to make drawings that are representing things correctly. That's not what we're going to talk about in this class. Partly because I'm not really good at that. Whenever I've had a job as an engineer, my job has been the idea guy. And I would make my rough sketch, and then we had somebody at the company that understood all the GD&T standards, and they would take my sketch and they would make it as a fancy drawing that met all the standards. And then they would ask me, is this what you meant? I would say, oh yeah, that's really good. And a lot of times, so I think it's going to be a mixed bag when you are in industry. You might be that. See, when I was a beginning engineer, CAD programs were sort of just getting out there in mainstream use. And so most of the times the drawings were done on paper or very early versions of CAD systems, and you had to be a real expert to drive one of those old systems. Today, everybody in here runs SolidWorks, right? Or some CAD software. And you can whip together a drawing in 2 seconds, right? So I think today they expect young engineers to do more of this. And I think it's problematic because do you know all the standard symbols? Do you know which one to use when? No. How are you going to learn? YouTube? Okay, when are you going to learn on YouTube? No, you're not. You're going to learn it on YouTube at the moment when you have to figure out how to put it on a drawing, right? All right, he's special. He watched. Who's do you like best? Whose videos do you like best? Okay, I get a recommendation coming up in the presentation here. Yeah, go ahead. I'm not sure I know that one. All right, so I want to focus on the tolerance side of GD&T. So the geometric dimensioning part, the GD part of GD&T is super important. I'm not an expert. I don't want to pretend to be an expert. And we can go to YouTube when we want to learn how. Later in the presentation, I actually have a recommended YouTube channel to look at. Or maybe it's right here. It's on the slides. It's on this slide. Nope. It's on this slide. This guy, R. Dean Odell. Go to his YouTube channel. He's the best at teaching that as far as I've found. So when you need to know that, and you will need to know that if you're the person responsible for making the drawing that's going to go out to the vendor. If you're the person responsible for the idea and the design concept, you won't necessarily need to know that. Okay, but how about the tolerance part? So we talked, last time we met, we talked about design for manufacturability, right? And so we started this topic of clearance for clearance holes. Because I said you, the designer, have to pick the dimension of the hole. But let's talk about the tolerances. So you've all seen this part? You've all seen this part? Anybody know what the function of this part is? Yeah. Not really. It holds the cylinder, right? It holds the cylinder. So our brass cylinder goes right in this part right here. And then there's a clamp, a strap that goes over the top, and two fasteners that hold the strap down to hold that cylinder in place. We call it a Y block. Why is that? Yes. Because it looks like a Y, exactly. It's the only reason we call it a Y block. It's very similar to a V block. So a V block would be sort of just this top part of the Y block, and use V blocks to hold round stuff. So it's just a fixturing tool in manufacturing. It would be a V. When you want to hold a round piece, you put it in a V block. We wanted a V block, but we didn't need all that extra material, so we made it look like a Y. Yep. Exactly. So you could, as long as your radius is not bigger than the height, or not, as long as it's not too big or too small. If you get too small, you get it lost in the bottom. And I mean, ours has a, I think it has a 1/4 inch radius at the bottom. But yeah, so when a V block, you can hold a bunch of different diameters, and it'll locate it either sideways in the vise or straight up and down in the vise, depending on how you orient the V block. Okay, so our Y block. So we know the, so what's the other function? So it holds the cylinder. So I'm going to talk about functional tolerances right now. So it holds the cylinder in place by allowing the strap to come down on top. What else does it do? Yep. So it attaches to the base. And so what it does is it locates the part of the cylinder that needs to get on, or needs to get warmed up, above the pocket that locates the burner, right? So that we can locate that spot above the fire. So it locates it in both Z and X and Y, and it holds the cylinder. So on my rough drawing here, you can see that every dimension that's called out has 3 decimal places. So there's 2.380, 0.500, right? All these dimensions that are called out have 3 decimal places. If you zoomed in on the tolerance block down here, you'll see that it says 3 decimal places is plus or minus 5/1000 of an inch. So any of those dimensions, so I'd be willing to take for this thickness 0.755 or 7.45? Yeah, 745. It's hard to go the other direction for me. It's easy to add, hard to subtract. So why did I, the designer, and sure, I'm the designer. I didn't make the drawing because I don't know how to do that, but I am the designer. Why did I, the designer, choose that tolerance? Right. So 10 within 10 thousandths of an inch, I don't care. Right. That's what the tolerance means. Why did I decide that?
Because with a small fonts like that, you'll still be able to have varying parts. Like if you make a part and be off by, like you'll make your half an inch bigger or smaller or whatever, but never that small difference.
So yeah, that's tolerances allow us to be able to not make the part exactly correct. Why did I pick plus or minus 5?
I was gonna say there's different types of fit, and there's like one of the clearance fits, no matter what the defense.
Well, so all right, so I set it here for my tapped holes. So I said what hole diameter to drill, and then what thread to put in it. And so here I'm willing to accept plus or minus 5 on the diameter of the hole. I'm willing to accept plus or minus 5 on the location of the holes in space, all the dimensions, right? Why did I pick plus or minus 5? 5 thousandths. Oh, in machinist speak, if we say plus or minus 5, we mean 5 thousandths. If we say 5 tenths, we mean 5 ten thousandths of an inch, 5 tenths of a thousandth. Yeah.
Is there an error specified for like each tool?
So there are some rules of thumb that you can find that different manufacturing processes can generally achieve specific tolerance bands or tolerance ranges. So yeah, there is, and it's within the band of our CNC machines for sure. The reason I picked plus or minus 5 is because I was being lazy. No other reason. I knew the machines could make plus or minus 5 pretty easily. Knew our measurement tools could measure plus or minus 5 pretty easily. And I really didn't care about any of the dimensions as long as we put quarter 20, well, this collet says quarter 20 holes. In production, we're now using, I think, 1024s. So we changed the hole size somewhere along the line. But I just didn't care. I was being lazy. And I knew that I had to give you some tolerance. So I put plus or minus 5 because it was easy for people to make. Is that a good way to pick tolerances?
Sometimes.
The answer is correct. Sometimes. Sometimes that's a good way to pick tolerances because sometimes it's good enough. And you don't want to do work that you didn't have to do. You want to do the right amount of work, right? So you don't want to overproduce. But if we were going to functionally tolerance this, so why do we care about this 0.996 width at the bottom? Why do we care about that? Because there's a mating part that it has to fit into, right? So we can't really design or can't really pick the tolerances for the mating part until we've designed this one and picked the tolerances, right? You got to do one of them first. Can't do them at the same because now that mating part can be 0.99. I know what's 5 plus 96. 101. So it could be 1.1. I can't do math in my head in front of the class. Sorry. It could be between the range of the smallest and the biggest, right? It has to be at least as big as the biggest possibility. And so we can co-design that. What else do we care about? What else do we care about on this part that we could functionally tolerance? So the location of the holes or the diameter?
Diameter, but I guess the location.
So really the location. So if I put the holes too close to the back edge, then the clamp would sit off the back of the part, right? If I put the holes too close to the front edge, then the clamp would sit off the front of the part. So what do I have to know in order to pick a functional tolerance for that hole location front to back? So, well, I probably want to dimension them from the center line. Ideally, I'd like to be at the center. But to pick how much off the center line is acceptable to me, what do I have to know? I need 2 pieces of information. Because we buy the clamps. So we're not making the clamps. I need to know what's the width of the clamp and compare that width to the width of the whole thing. So how much allowance do I have? How much could I possibly move it back and forth and have it not overhang the edge? And I need to know what the diameter of the holes inside is. Right? But mostly I need to know that width. So if we know some stuff about the part, we could pick some functional tolerances to help us design the part. But in this case, we didn't really care. So what do we do when we want to make our part better? So let's say we've been making these Y-block widgets for, I don't know, we've been making them for about 10 years, this design. And some of the new department head this year, new department head comes in and says, I want you to make a better Stirling engine. What's the first thing we could do to make it better? Oh man, you just said tighten tolerances with a reason. Within reason. Oh, within reason. So tighten up the tolerances. Right? Will that necessarily make a better part? No. So tightening is that was the reaction I wanted though. So thank you, sacrificial goat. I wanted somebody to say tighten the tolerances because that's the natural reaction, especially when we're young engineers, right? Why do we when we did the thing with what's the best car, a lot of people went to the Mercedes side. I think a lot of people went to the Mercedes side because they tend to design cars with tighter tolerances. And one theory is that when you have those tighter tolerances, the components last longer and things like that. The thing is, when you have those tighter tolerances, they're more expensive to make. And so, and they're more likely to fail with a little bit of wear. So I think you got to look both ways. But so just tightening the tolerance will not necessarily make a better part. I think you have to decide what defines better. And so it's a trick question. Okay, so what do you do? You're a young engineer. Yeah, you're a young engineer. You don't have to wait too long until you're an old engineer. You're a young engineer, and your boss hands you a part, a drawing for a part. I was going to say hands you the blueprints, but we don't do blueprints anymore. They attach a SolidWorks file, and they say, all right, here's the part. Here's the existing part. We need to add this new feature. And let's say the part, because I have an example, the part is the cover plate for the control panel for a 747 instrument panel. Right, so let's say you're Boeing, and you've got these instruments that go out. You've all seen the inside of one of these cockpits. Well, think it's an older one, not one of these new digital glass touchscreen ones. One of the ones with all gauges and stuff. And they have realized in the field that one of the gauges that's on there, occasionally you have to turn an adjustment screw on it. And to get to that adjustment screw, they have to take the whole panel off, set it on the pilot's seat, and then they go back there and they turn the screw, and then they put it back in, and then they turn something on and see if the adjustment worked. And it's a pretty crappy iterative process. And some mechanic says, well, hey, if we put a hole right here, we could reach a screwdriver in and turn that screw while it's still installed. It wouldn't have to do all that process. That's going to make the 747 better, right? It's going to make the airplane better. So you're the engineer that gets the job of adding that hole. And so you draw it, right? You draw that hole in, go through the engineering design process, and your new design gets sent out to the machine shop floor. And then they get the panel. They stamp all the holes in it for all the instruments and gauges and stuff. They take it out of the fixture. They bring it over to the milling machine. They get out their dial indicator and they indicate it in square. They get out their center finding tool and they find the center of one of those holes. And then they drill the hole that you put in. And then they bring it over and they go bring it in. And the mechanic's happy because he's got his hole. He can turn his thing. this true story. I'm not sure it was 747, but it was a Boeing product. Because the young engineer used a tolerance like plus or minus 5 on the feature that they drew in, because they were used to designing machined parts. But what they needed was more like, well, what they needed was, plus or minus a half an inch on location or something. And that extra step of moving to another machine to make that one hole in the thing. So the plane got better because we made the part better. But it also got $100,000 a year more expensive to make the plane. If we had done the correct tolerance on that hole, you could have just added another pin in the stamping process and not moved it to the machine. It wouldn't have cost any more to make. So small tolerancing mistakes can be expensive. Okay, what do we got next? Oh, tolerate. We've got this, right? And the definition in ISO is the allowable deviation from the standard. We've talked about all this stuff, right? We know what all this stuff is. All right. So here we've got tolerances indicated on the sketch. Let me put one of these up. Yeah, it's how much you're allowing yourself to screw up and still have a good part. All right, so we've got our part here. So what can anybody tell me about this part to start with? What kind of machine should we use to make it? Yep. Let's use a milling machine to make it. Okay. Based on what we know and what we've learned today, can we easily make this part in a CNC milling machine? Should be able to. Okay. So we've got plus or minus 5. So, all right, so let's, what feature should we make first? Yeah. You want to make the holes first? Okay. Which hole? Doesn't matter, right? All right, so let's make the top left hole. So I've made that hole. And what should I do next? Yep. So which one? Bottom left? Okay. So where is this hole? It's 4.109. Somebody got a calculator? $4.109 minus 1.352. So it's 2.757 plus or minus what? Is it 005? Okay, so in the Haas machine, so you've got like the memory and the edit and the DNC and what's below that one? Handle jog, and then home, and then list programs. I think those are the mode selection buttons on the right-hand side. Third one in, next to the edit button, is the undo button. So we'll go ahead and press the undo button. it loads a welder into the spindle and it fills in the holes again. You guys are supposed to laugh at that. The undo button does not load a welder into the spindle and fill in the holes again. It would be pretty cool, but no, the undo button just undoes like the last text thing you did. If you did a text thing. Okay, so you want to make this. You want to make this corner first. Is that what you want to make first? Okay. All right. So I want to make the part be this dimension. And so what's the process you're going to use to make that? Yeah. Like those skinny girl martinis, right? The skinny vice. Yeah, so if it was a larger piece than your vice jaws, and you could get a skinny vice that could do this, you could have a tool path, and so I might orient it the other way. I'm not going to change the board orientation here. Wait, does this work? No, it's not a touchscreen. Right, but if we would hang it out both edges of a vise, and then we could have a program that does a contour on one side and a contour on the other side. Okay, what if we can't do that? What if we don't have that skinny vise? Yeah, so I could make one side flat and smooth. I could do it by sticking the part up in the vise and doing a facing operation. I could do it by having the part hang out the edge of the vise and doing a contouring operation. I could do it by, I don't know, very patiently pushing it up to the sander and making it square. Don't do that last one. Right, so I make one side square. Is that good? Now what? Flip it over, make the other side square, and make sure that it's the right distance from the other edge. All right, so I can do that by sticking it up, facing it, flip it over, and face it. What if I wanted to hang the edge out of the side of the vise? Instead of doing the facing operation, what if I wanted to use a contouring operation to do the second side? Yep. And I would have to make sure that these edges were perpendicular to this edge, right? So it would have to be perpendicular and square, or perpendicular and, I guess if they were both perpendicular, they would be parallel, right? And then you can turn it sideways. So if you had a piece of stock that you knew was square, you could make one side the right distance away from the other side. If you didn't know that it was square, I think we got to do the stick it up, face it off, flip it over, face it off. Okay, so now we've got two parallel sides. What's next? I got two parallel sides because we stuck one side up, faced it, flipped it over, faced it at the right height. Yep.
Now, there's also another set of two parallel sides, but one of them is kind of chipped off the corner.
Well, we don't actually, this might be bandsaw cut on the edge right now. I just have two sides that are, what are they? 1352 plus 4109. Somebody had a calculator. So this dimension is 5461 plus or minus 10. Because those two fives add together or subtract together. Okay, once we made those two sides parallel, what's next? Now I think it's where we get our skinny vise. Now we can put it in the skinny vise because we've got two parallel sides, and we can make those dimensions, whatever it is. This one is, oh, it's already plus or minus 10. Look at that. They were thinking. 5, is it square? Nope. Oh, maybe. Really? All right, so we can make our other parallel sides. And so what's this dimension? So it's 6.
I'm sorry, I can't do that for you.
Never mind. My inner 13-year-old almost jumped out and said something back to her. What? Yeah.
So the bottom and top are apparently what? The bottom is 6.551.
6.551.
The top is 5.357, but like you have a portion of it is chipped up.
And that's plus or minus. So plus or minus 5. And yeah, but that's not to this edge, right? So we've got something going on here. So how big is that? What is that, a chamfer? It's kind of a giant chamfer on that corner, huh? How big is that chamfer? Yep. This is the dimension you're talking about?
Yeah.
1 point what?
194. We could probably do like a 1 or plus.
Well, so, and this is not a real dimension on the part, because if we add that dimension on the part, then we've over-constrained it, correct? Because if we add that dimension to the part over here, then the tolerances can't add together. Okay, so now that we've made our square part, squarish part, now you want to make the holes? Anyway, the point of this exercise is to catch that you have to add these together to catch the plus or minus 10 here and 5 here. And so the tolerance on this distance has to account for that difference. So there's a little bit of a conflict in there. It's pretty normal, and this is a simple part, right? It's a rectangle with 4 holes and a corner chopped off. So as you get to more complex parts, the way these things add together is important. Why would you dimension the holes from each other instead of from the edge of the part? Why didn't you just dimension both holes from the edge of the part? Why do we dimension one hole from the edge and then the other one? Right, because the hole pattern is more important to us than the distance from the edge of the part. That's why we dimension the holes from each other instead of from the edge of the part, except on the dimension, both the top and the bottom holes are dimensioned from the edge of the part, and the width between the holes is dimensioned from each other. Anyway, the way you put the dimensions and the tolerances on the page, yeah.
Is it then fair to assume that there's going to be like two things that have like two prongs, or like the holes? I don't know how to say this, but like,
Yeah, I know exactly what you're saying. It seems to be that there's two independent functions of those two hole patterns. There's two different hole patterns that have an independent function of each other, and there's two different things clamping onto the back of it. And this is another thing. When you're the manufacturer and you get a drawing from somebody, it almost never says on the drawing what the part is or what it's for. Right? They give you a drawing and they say, I want a part back that's this shape. Especially, we've done a bunch of defense work in the past. They won't, it's for an aircraft, but they won't tell you which one. Right? And it's kind of funny because then you go to the guy's office and there's only pictures of one aircraft on the wall. So you pretty much know which one it is. Anyway, intolerance will not be tolerated. So you can do functional dimensioning and tolerancing by figuring out how does everything have to fit together. We've talked about that a little bit. What if you just want to pull it up out of a cookbook? Right, we could just make it up. We could just say everything's plus or minus 5. That will work in many occurrences. But what if we wanted a press fit? So what if I wanted the bottom holes to be a press fit and the top holes to be a slip fit? So the top holes were for locating something and the bottom holes were for holding it together.
Well,
Yep.
I was gonna say like one example of the qualities. I actually learned the cylinder when I was in the cylinder. That the piston was too big for my cylinder to fit in. So I was thinking like make the cylinder like hold the cylinder a bigger tolerance or make the piston smaller tolerance.
So that piston cylinder interaction is actually a functional tolerance. And if the one you made didn't work, it had something to do with the measurement or the setup of the machine, not the design. For sure. But you had.
Yeah, so to find things like press fit, there are manuals or websites that you can use that are pretty cool. And you have to do
So you can go to the Machinery's Handbook. I think we showed you the Machinery's Handbook earlier in the class. So you go to the Machinery's Handbook. You can do, what's the section called? So in the GD&T section, you go to allowances for tolerances and fits. So who's heard of shrinkage fit? So how does it work? So it works because of thermal expansion of metals, right? So you make a hole and you warm up the hole. You make a pin that goes in the hole and you cool it down. Then you stick them together and the cool pin warms up, the warm part cools down, the hole shrinks because it's cooling down, the pin expands because it's warming up, and they come together like that. So you can design how small does the hole need to be, how big does the pin need to be, it depends on the different materials, and how much force do you want that fit to withstand. So once you put it together like that, how do you take it apart? Yeah, bigger hammer is the only way, right? You have to break it. So those are really good for permanent things. So we got running sliding fits. Running sliding fit is when you want it to go in and come out easily. A press fit is when you want to have to use force to push it together. And so if you go to the Machinery's Handbook and you look for the allowances for tolerances and fits, if you know what size either the hole or the shaft is, you can then dimension the other part and put the correct tolerances on it so that it works every time. So when you're doing your MQP and you need to put a pin in to locate something, how are you going to figure out what size the hole needs to be? So, say it on 3. 1, 2, 3. It's pretty sad. All right. This side of the room versus that side of the room. 1, 2, 3. You guys wake me up when you're ready. All right, so we're going to look it up in the machinery's handbook. Hey, what are we going to do tomorrow? I'm going to get a whole bunch of machinery's handbooks and lay them out on the table and make you guys look stuff up. That's what we're going to do tomorrow. That's what we're going to do tomorrow. Be prepared to go to the library's website on your computer or your smart device or something like that. And we are going to have a competition in our groups to look stuff up from the machinery's handbook and to find stuff out. Scavenger hunt. Machinery's handbook scavenger hunt tomorrow. Be prepared to use a digital copy or a physical copy. I don't care. If you have a physical copy and you want to bring it, that's fine. I might bring a couple physical copies. I have several editions. But you can get it from the library on the ebook. That's what we're going to do. And so a week from today is our final presentations, right? Week from today is our final presentations. You looked questioning when you were looking at me. That's why I was asking. I was asking everybody. All right. I'll see you all tomorrow. Be prepared to look stuff up. If you guys had shown a little bit more excitement, I might have not had tomorrow. Look at that. Oh,